These are our notes on specifically discussing the 4 types of intermolecular forces. So we'll start with ion-dipole. This is our strongest intermolecular force. And the ion-dipole forces are the electrostatic attraction between an ion and the oppositely charged end of a polar molecule. Most of the time when we talk about this, we're going to talk about water and a salt mixing together. And so when we talk about ions in water, we're going to have the negative oxygen side attracted to the positive ion in the ionic bond, so in the salt. And so here, potassium chloride we know is a salt because it's a metal and a nonmetal. And so the negative side of the oxygen molecule, because it's got a higher electron density, because it's more electronegative, it's going to attract those electrons a little bit more. It's also got those lone pairs, is going to attract the potassium more than the chlorine would. So even though the chlorine is negatively charged, potassium will like oxygen more as soon as it gets into the water. And then vice versa, chlorine likes hydrogen more, so the hydrogen, the positive ends of hydrogen, are going to attract that negative chlorine ion. So this is why we say that ionic bonds dissolve in water, because they actually are being surrounded by those water molecules. Covalent bonds don't dissolve in water because they aren't charged. They're true bonds, so there's not a positive and a negative end, and so there's no attraction between the positive and negative hydrogen or oxygen with a covalent bond, but an ionic bond has that attraction. And so when we have this energy here, we call it, this interaction actually releases energy, and we call it the enthalpy of hydration. And we're actually going to study this and be able to calculate the math with this in the solutions unit, which is coming up after liquids and solids. Our next interaction is a dipole-dipole force, and these are the electrostatic attraction between oppositely charged ends of polar molecules. It is our 3rd strongest intermolecular force. So an example here is hydrochloric acid, or HCl. So the attraction of the hydrogen, positive hydrogen, and negative chlorine are going to attract each other. And that is what we call that dipole-dipole force. And it's really important that you're able to figure out the electronegativity differences from the bright yellow table that we learned during the chemical bond unit, to be able to figure out if you've got that electron density difference where you're going to have electrons hanging out more around the chlorine, which is why it's a little bit more negative. Water is actually an example of a dipole-dipole force, but we know it's a hydrogen bond, and a hydrogen bond is actually just a stronger dipole-dipole interaction. I don't know if you remember us talking about that from first semester. We will revisit that idea in just a second. So, let's talk about this idea of polarizability. So polarizability is the tendency for the electron density of an atom or molecule to be disformed or sloshed around, deformed or sloshed around. So polarizability will increase with an increased mass, a greater number of electrons, and where electrons are less tightly held. So think about if you've got some electrons moving around an atom. We know, because of Heisenberg uncertainty principle, we don't know the speed or the location of any given electron at any time. And so sometimes there could be a greater electron density on different sides. And so when we have polarizability, something with more mass, something with more shells, something with a greater number of electrons is going to have electrons that are more polarizable and more sloshable, if you will. And so they will actually have more moments, more dipole moments. So polarization of molecules or atoms results in what we call instantaneous dipoles. Instantaneous dipole moments are due to the polarizability of the molecule. So iodine, for example, has no permanent dipole because it's nonpolar. So normally iodine looks like that. But because electrons can be circling around the nucleus anywhere they want to be in those orbitals, we could have moments of polarity, is what we call it. So moments of polarity where I might have a few more electrons circling around this atom than this atom, and then maybe that's also happening here. There is a momentary attraction between these two molecules. Polarizability is important because we connect it to London dispersion forces. So London dispersion forces are the electrostatic attraction involving instantaneous dipole moments in nonpolar molecules. So the greater the polarizability of the molecule, the stronger the interaction. We know that our London dispersion forces are our weakest intermolecular force, and it's because most of the time when we're dealing with London dispersion forces, we're dealing with molecules that are nonpolar. Even though all molecules are polarizable and all molecules experience dispersion forces, we address dispersion forces more with nonpolar molecules. So if I'm looking at this example, which would be affected more by London dispersion forces, hydrogen or iodine? So hydrogen, if I'm going to count the electrons, hydrogen has 2 electrons and iodine has 106 electrons. So we've got to ask ourselves, which would be more polarizable? Because iodine has more electrons, this would, quote, slosh around more and have more moments of polarity. So the iodine would be more affected by London dispersion forces. Hydrogen bonding is our second strongest, so it's an interaction that exists between the hydrogen atom in a polar covalent bond with the fluorine, oxygen, or nitrogen, and the lone pair electron on a nearby highly electronegative atom. So fluorine, oxygen, or nitrogen. I like to think about it as NOF, N-O-F. It's a little bit easier for me to remember that way. This is a special case of a dipole-dipole interaction. Since hydrogen always shares all of its electrons with positive nucleus, it is relatively exposed and attracted to unshared electron pairs on another molecule, which is why, even though this is a dipole-dipole force, it is considered its own type of intermolecular force because of that hydrogen there. And so the hydrogen bonds are much weaker than covalent or ionic bonds, but they are actually stronger than dipole-dipole or dispersion forces. So that's why we used to think it was our strongest. Ion dipole is actually a little bit stronger than a hydrogen bond, though. And hydrogen bonds are strong enough to determine the structure of ice and proteins. So one way that you will always know that we're showing that we have a hydrogen bond is the ... here. So here's our water molecule, here's our fluorine, hydrogen and fluorine, hydrogen and oxygen on another molecule, hydrogen and nitrogen on another molecule. So that's where the NOF comes in. And again, that hydrogen attraction, it's just showing lone pairs connecting with that other molecule. So just super important, that ... is what that's showing. So the cool feature of water is that this allows the solid crystal form or solid water, i.e. ice, to be less dense than liquid water, and that's not true for other solids. And it allows ice to float and fish to live at the bottom of a lake in the winter when that water freezes. So the reason why the water does that is that it actually creates a hole in the middle. And we drew this in the first semester, so let's draw it again. So we're going to start, and I'm going to draw my water, and I'm going to draw it like that, kind of at an angle, and then draw a ... and connect it to another oxygen. So here's that connection between the lone pairs on an oxygen with the hydrogen. And then I just kind of am going to draw around, one goes over, and then one goes down. And I'm going to continue my circle, one goes over, one goes down, just showing you this is how water molecules structure themselves when they freeze. And what actually happens is it creates an air pocket right in the middle. So again, this is why ice is able to float on top of liquid water. So that structure of that hydrogen bond allows for that to happen. Okay, here's your video set on the different intermolecular forces in the examples.